Hello. In this video, we are going to attempt to derive a wave function solution for the two-dimensional particle in a box problem. Previously, you'll have seen in the video, and you can see the link up there, we derived a solution for a one-dimensional particle in a box. In this case, we're going to two dimensions. So we imagine that the box is a rectangle. Along this coordinate, we go in the x direction with a certain length L sub x. In this direction, in the y coordinate, we go from the origin out to a distance L, and that length would be L sub y. We can imagine that this is a Cartesian coordinate system, the plane R2, and that we're confining our solution and just setting up our problem in such a way that the problem is entirely at the origin and in the first quadrant. Recall that any system will satisfy the Schrödinger Equation, which in general is minus h bar squared over 2m times del squared, the Laplacian, times psi, plus some potential times psi equals E times psi, where E is the energy of the system. In our particular case, we are going to follow what we did for the one-dimensional case and imagine that the particle is confined to the box by having outside the box a potential that is infinitely large. But inside the box, the potential is zero, so that within the confines of the box, the particle is entirely free to move. So with that in mind, and using the fact that we are now in two dimensions, we can write the appropriate Schrödinger equation as minus h bar squared over 2m times the second derivative with respect to the x coordinate plus the second derivative with respect to the y coordinate acting on psi. And this is going to be equal to the energy of the system times psi. In cases like this, where we have, essentially these are partial derivatives. I've written them as ordinary derivatives, but they'll be partial derivatives. This type of problem is called a differential equation. And since it will involve partial derivatives, we call them partial differential equations. It turns out that there are not many techniques to solve partial differential equations. Therefore, we shall use the most common and most effective technique, which we call separation of variables. In ordinary differential equations, separation of variables is only useful for a very limited number of equations. With partial differential equations, on the other hand, this is very often the most useful technique that we will use. So, if we decide to do that, what do we do first? The key feature of using separation of variables to solve this particular equation is to make the following assumption. So we're assuming. So we're assuming that we can write the wave function solution in a very, very specific form. We're assuming we can write it as a function entirely of x, which I've kind of written as a big stylized x there. And I'll emphasize this by showing that it's a function of x times a function of y. It's entirely a function of just y itself. This is an assumption. If it turns out that there is no valid solution of this form, we're out of luck. At least for as far as we know right here. But we're going to assume that we have such a wave function solution, and then proceeding from that assumption, try to determine exactly what that wave function psi will look like. If the wave function psi that we've selected is truly a solution of the Schrödinger equation, then it has to solve the Schrödinger equation. So that means at some point we have to determine these derivatives. The partial derivative with respect to x, and the second partial derivative with respect to y. So let's see what those particular derivatives will be. So if we take the second derivative of our wave function, which we recall is a function of x entirely multiplied by a function entirely of y. Well, since we're taking the derivative with respect to x, any function that's entirely a function of y alone is not affected by the differential operator. So, since the fact that the differential operator is a linear operator, so we can pull the function of y out in front and then proceed to take the second derivative with respect to x. Now we don't know this particular form of that derivative, so we'll just write it as the second derivative. So this is the function y times the second derivative of x with respect to x. Similarly, we need to determine the second derivative with respect to y. Of psi. So it's x of x times big Y of little y, if we want to say it that way. And similarly, for the same reasoning that we used here, if we're looking at the derivatives with respect to y alone, any function of x by itself is not going to be affected. So this acts as a constant when we're taking partial derivatives. So we pull this to the front. And then we take the second derivative with respect to y. So now, what do we get in our Schrödinger equation? Well, we had the factor in front of minus h bar squared over 2m. That stays the same. So now we replace it with the appropriate second partial derivative. So we have big Y of y times the second derivative with respect to x. Plus the function x of x times the second derivative with respect to y alone. And this is all going to be equal to e times psi, which is simply big X of x times little y of y. Now, it may appear that we have not particularly helped ourselves by rewriting the Schrödinger equation in this particular form. But let's see what proceeds from here. So the next thing we want to do is the one step in the derivation which might seem bizarre and surprising, which is to multiply each side of the equation by 1 over big X of x, big Y of y. So we want to multiply 1 over x, y, both sides of the equation. Now if we do that, we get the following result. Minus h bar squared over 2m. Then we get 1 over big X of x times the second derivative of x with respect to x plus 1 over big Y of y times the second derivative of y with respect to y. And then the right hand side, because we divide it by big X of x, big Y of y, we get simply e on the right hand side. And that is the key feature of the derivation. And it's a key feature for the following reason. Here we have a function entirely of x. So we have 1 over x and then multiplied by its second derivative. This term here is a function entirely of y. So we have 1 over y of y and then a second derivative with respect to y. So we have function simply of x and a function simply of y. And it turns out their sum turns out to be the energy, which is a number. which is a constant, which is not a function of x and is not a function of y. Why do we insist upon that? Well, let's change x. So we're going to hold y constant, and just change x. Now, if y is constant, that means that the derivative with respect to y is 0, so we can think of it as just dropping this term out at that case. So, if we set y to be constant, then and just change x here, that means that 1 over x is equal to a constant. So, no matter how we change it, no matter how we change x around, we still get the same constant on the right-hand side. So that tells us that 1 over x times the second derivative is equal to a constant. So let's say that that constant, we'll call that constant E1. So that tells us that minus h bar squared over 2m times 1 over big X of x times the second derivative of big X of x with respect to x is equal to a constant, which we'll call E sub 1. Next, we set x to be constant. Therefore, this particular term drops out. And we notice that we have a function entirely of y, which again is equal to a constant on the right-hand side. No matter how we change y, we still get a constant. So that tells us that this term must be equal to a constant, which we're going to cleverly call e sub 2. So, very similar to what we did here, except applying to y now. So we have minus h bar squared over 2m times 1 over big Y of y times the second derivative of big Y of y and again this is going to be equal to a constant which we're going to call E2. Now we notice something quite interesting, and we'll just look at it for the case of y. So now that we've been able to break our original equation, Schrödinger equation, into two equations, one that just involves x, which we've written in blue, and one which just involves y, which is written in orange. So let's continue with this equation and simply multiply both sides by big Y of y. What do we get in that case? Well, we get minus h bar squared over 2m times the second derivative of big Y of y is equal to e sub 2 times big Y of y. And we should notice something here. That if we simply consider big Y of y to be psi, we have the Schrödinger equation for a one-dimensional particle in the box here, where our solution psi is simply big Y of y. So that tells us that the solution to the y part of the Schrödinger equation, or big Y of y, this is equivalent to our psi, if we want to think of it, for a one-dimensional particle in the box in the y direction, and we know what the solutions are. We've already derived those. So we can write down that solution on site. So we have minus the square root of 2 over the distance in the y direction times the sine of, now we have to use different n's because first we'll have an n that just involves y. So we have n sub y times pi times y. And it's all divided by the length, and the length in the y direction is L sub y. And then we know that the possible values of n or n sub y will be 1, 2, 3, for example. So we know what the solution is in the y direction if we have a one-dimensional particle in the box that goes in the y direction. And what we achieved was, by starting with the assumption that we could write the wave function solution in a very particular form, we were able to break one very complicated Schrödinger equation into two Schrödinger equations. One we just solved, the one in the y direction, and we recognize that it's a one-dimensional particle in the box problem, and we're able to write down the solution by sight. Can we do the same thing for x? Yes, because if we take our x solution, we'll show how we do that, it proceeds exactly the same sort of way. We take our blue equation, which I just erased, but you can always rewind the video to remind yourself of what we had written down in the blue case. Again, if we multiply both sides of that equation by big X of x, we get a Schrödinger equation in one dimension, which looks like minus h bar squared over 2m times the second derivative with respect to x is equal to e sub 1 times big X of x. And this is simply the one-dimensional particle in the box problem in the x direction. So we're able to write down the expression for big X of x, which is essentially the psi solution for this particular Schrödinger equation. We've already derived that before, so that's square root of 2 divided by L sub x times the sine of, now n sub x, we have to be careful here. Since we are in two different dimensions, we have two different quantum numbers n. One n which is applicable to the y direction, and one that's applicable to the x direction. And that's the only slight difference that we're making from the pure one-dimensional problem. And also, we have lengths. So instead of just having a length L, which was our length in the x direction before, we have a length in the x direction and a length L in the y direction, and they need not be the same. So we can solve the problem for a particle in a rectangular box, and then the answer for a square would be just a special case of that. So here's L sub x. And again, the n sub x's are going to be 1, 2, 3. So in summary, what have we done so far? We were able, by assuming that the wave function solution for the two-dimensional particle in the box had a very specific form, we were able to break it down into two different one-dimensional particle in the box problems, one in the x direction, one in the y direction, both of which we know how to solve. So we were able to write down the wave function solutions directly. So what does that tell us? Well, it tells us that our assumption that we could write the wave function solution in a very specific form turned out to be true. So it turns out that the wave function solution in two dimensions is simply x times y. In x, so we'll write down the x part here. So that's the square root of 2 divided by L sub x times the sine of n sub x pi x over L sub x. So that's the part that has to do with the x sub x part. And then multiplied times it, we have the y part, sorry, yellow here, which is the square root of 2 divided by L sub y times the sine of n sub y times pi y divided by L sub y. And the n's, so n sub x and n sub y, so n sub x is 1, 2, 3, and n sub y is also some combination of 1, 2, 3. What we haven't written here is one final result. This is the wave function solution. The energies are trivial to find. The energy with respect to x is simply e sub 1. The energy with respect to y is e sub 2. So the overall energies are going to be e sub 1 plus e sub 2. E sub 1 is the energy with respect to x. And we already know that those are going to be the n squared, but now n sub x squared times h squared over 8ml sub x squared. So simply take the solution that we already know for the one-dimensional particle in the box, but we're just very careful to put the proper subscript. So for n we need n sub x, and for L we need L sub x. Similarly, the energy E sub 2 is the energy with respect to y. So we have n sub y squared, h squared, divided by 8m L sub y now. So we have to replace it with L sub y squared. And since the energy is since we wrote it as a separable function where we multiplied a function of x times a function of y, one of the beautiful results of those types of solutions to a differential equation is that the energies are going to be added together. So if we have a wave function solution that we get by multiplying two functions, the energies are going to be added together. So the total energy is simply E sub 1 plus E sub 2. And that's going to give us, now we can factor out certain factors here so that we get n sub x squared plus n sub y squared divided by L sub x squared plus L sub y squared, and then h bar squared, a squared, divided by 8m. And this gives us the total energy for a two-dimensional particle in the box with lengths L sub x in the x direction, L sub y in the y direction, for the quantum numbers n sub x and n sub y, which are equal to positive integers. I thank you very much for your attention. Have a good one.